I want to take a look at section 3.7, number 14 of Stewart's calculus textbook. It says a stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. Find the rate at which the area within the circle is increasing after 1 second, 3 seconds, 5 seconds. What can you conclude? Okay. So let's see if we can do that calculation. So I've got drop that hits right there, and then everything travels outwards. This would be the radius of that circular ripple, but everything is moving outwards. Okay. Now, first of all, it says the radius is increasing at 60 centimeters per second. So I think what I can say here, let me see if I can justify this, is that the radius is equal to 60 times t, right? At time 0, you're going to have a radius of 0, and then 1 second later the radius will have increased by 60. So 1 second later you're going to have a radius of 60, and that when t is 2 you're going to be up at 120. So every second you're going to gain 60 centimeters. Notice that's actually a rate of change already. That dr dt is 60, oh goodness, come on now, is 60 centimeters per second, right? That just from the point of view of looking at a function here, the derivative of 60 times t is 60, and so, but this is 60 centimeters per 1 second. Okay. Now, what I'm really interested in is the area, and I happen to know that the area of a circle is pi times the radius squared, so plugging that in now, so I have the area as a function of time. This is pi times 60t squared, so this is, the area is 3600 pi times t squared. So now I can talk about the rate at which the area is changing. Because I have the area as a function of time, I can say that dA dt, the rate of change in the area with respect to time, is the derivative here. So bring the 2 out in front, so this becomes now a 7200 pi times t, right? And the area is measured in, well, the radius was centimeters, so this was now square centimeters per second. Okay. They asked me about 3 different times. At t equals 1, dA dt is, just plug a 1 in there, 7200 pi times 1. Right? When t equals 3, you've got dA dt is 7200 pi times 3, which is substantially bigger than that, right? This would be, there's a pi times 0 times 0 times 6 times 21, right? So this, at time 1, you're gaining 7200 pi centimeter, square centimeters per second. At time 3, you're gaining, 3 times as much. This is in centimeters squared per second. And at time 5, you're gaining even more area per second. Oops, not 4, 5. dA dt is 7200 pi times 5, which is 36,000 pi square centimeters per second, right? It seems that as time goes on, the area is changing faster. Well, I think that makes some sense if this circle is gaining the same amount. So if every second you gain 60 centimeters, is that what it was? Every second you gain 60 centimeters. Well, if the radius is here and you gain 60 centimeters, then all of this area was the new area. It's the change, right? So in 1 second you gained that area. Well, for the first second you only gained this much area. Right? For something later on, when the radius is already really big, you're going to have a particular circle here, and all of a sudden I'm running into myself. So let me move this down. So it's, when r is big, you're clear out here, and then you change by 1 second, you gain your 60 centimeters, and then the area that you're gaining is so much bigger that this area here, this gain in area in that second, is much more than the gain in area down in here, right? And even more so than down in there. So the bigger the radius you start with, the more area you're going to gain in that next second. Okay, so there you go, a rate of change in the area with respect to time.